Hi everyone, my name is Bianca. I'm a senior software engineer and Unity's resident expert in all things accessibility. I lead the development of our screen reader support on mobile and desktop platforms. But I want to start somewhere else, a time before I wrote my first line of code. Disability has always been a part of my life. Growing up, I wore glasses. Without them, I couldn't see past my hand. My brother has Down syndrome, and honestly, none of that felt unusual to us. That was just our normal. What did feel unusual was noticing how differently people treated my brother. He found his refuge in games, even though he could never finish any of them because they weren't accessible for him. Unfortunately, his barriers don't have a fix. What has a fix is the level of accessibility in games. Years later, when I joined the accessibility team at Unity, I expected the challenge to be technical. And it was. But the first thing I noticed was that my colleagues didn't know that there's an entire infrastructure sitting underneath every platform, waiting for apps and games to connect to it. I call it the shadow interface. Then I realized our testers had a different problem. They understood what to expect in theory, but they had never used a screen reader before. And once they activated it, they were lost. Today, I'll try to fill this gap on two sides. Developers who aren't aware of what screen readers need from an application, accessibility experts who don't always understand why implementation is genuinely complex. Both sides of the same coin. So here's what I want to do in the next minutes. I'm going to explain to you how screen readers actually work across ecosystems: mobile, desktop, web, and games. I'll tell you about the invisible infrastructure that mobile and desktop platforms have spent more than 25 years building. Then I'll explain what happens when you look at games through that same lens. And what I hope you'll understand is that the gap is real, but it's closing fast, and the tools to close it further have never been better. This talk is not a deep dive into code, APIs, or specifics of how to implement screen reader support. I've already presented an in-depth technical dive into Unity's accessibility APIs at Unite 2025. The presentation is called Reach New Audiences with Accessibility and Localization in Unity 6, and it's available on YouTube. My hope is that this talk becomes something you share with your friends and colleagues, whether they're engineers who've never used a screen reader or accessibility advocates who'd benefit from a clear picture of why implementation is so cumbersome. This talk aims to be a bridge between both sides. You build an app. Maybe it's a mobile app or desktop tool, or maybe it's a game. You've spent months on the user experience, every button, every menu, every animation tuned to feel just right. You ship it. But here's something almost no one tells you during development. The moment your app starts, the operating system builds a second version of your entire interface. A parallel structure, a simplified, organized description of every element on the screen. What it is, what it's called, what state it's in, and what a user can do with it. This shadow interface exists on most platforms you can think of: iOS, Android, Windows, Mac, and web, to name a few. If you're a developer, you've probably never seen it unless you intentionally looked for it. I know I haven't. For the accessibility experts, most assistive technologies rely on it, but you may have never understood how it works. And if you're building games, and this is the part that matters most for this crowd, your engine has probably been ignoring it entirely for a very long time. Today, I hope I'll be able to make this invisible layer visible for everyone. Screen readers are just one consumer of the shadow interface. Many assistive technologies draw from the exact same accessibility hierarchy. Build it well once, and all of them benefit. Break it, and every single one of them breaks in its own way. Refreshable braille displays sit at the end of a chain. The screen reader queries the hierarchy, formats the output into dot patterns, and pushes it to the display. A button without an accessible label renders nothing. Speak screen and select to speak pull text from your hierarchy's values, not from pixels. When your label says one thing and the screen says another, the user hears words that don't match what they're looking at. Hover text magnifies what's under the cursor reading from the accessibility hierarchy, not optical character recognition. If your text lives in pixels rather than hierarchy nodes, it does not exist. Switch control auto-scans through your hierarchy node by node, one switch press per element. Every element you fail to group makes the navigation path longer. Eye tracking resolves gaze coordinates against the hierarchy to identify what the user is looking at. If an element is not marked as accessible, gaze-based snap to item cannot find it. Zoom with follow focus subscribes to focus events in the hierarchy to move the magnified viewport. When focus lands on an inaccessible element, the viewport doesn't move. The element is invisible until the user manually scrolls to find it. Voice control maps spoken commands directly to accessible names. Say, click submit, and voice control scans the hierarchy for an interactive element named submit. An icon-only button with no label forces the user to say, show numbers, locate a numeric overlay, and say, click 14. 3 steps instead of 1. One hierarchy, 7 technologies. The same missing label, the same wrong order, each produces a different failure. That's the real cost of an incomplete or missing hierarchy. It's not one broken experience, it's at least 7. Now, let's start with the core idea as everything else builds on it. When you open an application, the operating system doesn't just render pixels. It also constructs a data model of the interface, a hierarchy of elements where each element represents something meaningful. A button, a heading, a text field, a slider, and so on. Each node carries a set of properties. A role, what is this thing? A name, what is it called? A state, is it checked, expanded, disabled? A value, what the current number on this slider is, and more. This is called the accessibility hierarchy. And it's the actual interface that screen readers and other assistive technologies consume. Not the pixels, not the visual layout, the hierarchy. This is worth sitting with for a second because it reframes everything. A screen reader is not reading your actual screen. I know, the name on the tin doesn't match what's in the can. It's actually reading a structured description of your screen that the operating system maintains in parallel. If that description is empty, if you don't feed it, the screen reader has nothing to say. Most people, the first time they imagine a screen reader, picture someone listening to the entire screen read top to bottom. Nobody uses a screen reader like this. That would be like reading a website starting at the logo and reading every word through the footer. It doesn't make sense, so nobody does that. On desktop, screen readers like NVDA and JAWS operate in something called browse mode. They create a linear text version of the interface and then give the user single-key shortcuts to jump through it structurally. Press H and then jump to the next heading. Press B to the next button. Press F to the next form field. Press 1 through 6 and you jump to a specific heading level. According to the WebAIM Screen Reader User Survey, more than 70% of screen reader users navigate by headings first when looking for information. They're scanning structure, not listening linearly. On iOS, voiceover users navigate by swiping right and left to move between elements. But the game changer is the rotor, activated by rotating 2 fingers on the screen. The rotor lets you pick a navigation category, headings, links, form controls, and then swipe up and down to jump through only those elements. It's like a drill-down filter for the interface. On Android, TalkBack uses a similar model. Swipe right or left to navigate, double tap to activate, and reading controls, a 3-finger swipe, let you cycle through navigation categories. Here's the point. Screen reader users are power users. They're navigating at speech rates of up to 800 or even 1200 words per minute, more than 5 times the normal human speech. They know their tools in and out. Almost 60% self-rate as advanced users. The bottleneck is almost never the user. It's almost always the quality of the data in the accessibility hierarchy. If your headings are wrong, heading navigation is useless. If your buttons are unlabeled, button navigation announces nothing. Screen readers are precise. They just need accurate data. Here's where it gets interesting or frustrating for developers. Every operating system agrees that this shadow interface should exist, yet each one built its own version of the plumbing. On Windows, the history goes back to 1997 with the world's first platform accessibility API called MSAA, Microsoft Active Accessibility. In 2006, that evolved into iAccessible 2, an open standard led by IBM. Wait, it gets even better. Then Microsoft introduced UI automation. Today, screen readers like JAWS and NVDA primarily use iAccessible 2 when talking to browsers and many desktop applications, while Narrator uses UI automation. Two APIs, same platform, doing roughly the same job. On macOS, Apple introduced the NS Accessibility Protocol in 2002. Apple Screen Reader queries your application's interface element by element. It asks, what elements do you have? What are their attributes? On iOS, the system is built on the UI Accessibility Protocol. Every element can declare itself accessible with a property called isAccessibilityElement. It exposes a label, a set of traits, which is Apple's word for role encoded as a set of flags, and a value. When something changes dynamically, the app posts a notification and VoiceOver announces the change. This is the iOS equivalent of a live region on the web. On Android, TalkBack is built on the Accessibility Service class. It receives accessibility event objects whenever the UI changes and queries the view through accessibility node info objects. Content descriptions, state flags, bounds, available actions, all structured data. And on the web, the same principle applies, just with the browser acting as the middleman. When a browser loads a page, it doesn't just build a DOM. It builds a parallel accessibility tree derived from the DOM but stripped of visual noise and enriched with semantic information. A button element automatically maps to the button role. A nav becomes a navigation landmark. Screen readers like NVDA and JAWS consume that tree, not the page you see. This is actually the version of the shadow interface most developers have at least heard of, and it follows exactly the same pattern as every native platform. The browser builds the tree, the screen reader reads it. The developer's job is to make sure the tree has branches and leaves. Each platform has its own quirks. More platforms, more implementations. One shared principle. The OS, or in the web's case, the browser, maintains a parallel structure description of every interface, and assistive technologies read the description, not the pixels. For the accessibility experts, this is why implementation is genuinely complex. It's not that developers don't care, it's that make it accessible means learning a different API on every platform you ship to, each with its own quirks, its own naming convention, and its own model of how to describe the same button. For developers, this is why accessibility experts get frustrated. The infrastructure exists. The screen readers are sophisticated. The missing piece is almost always the data your app feeds to the operating system. Let's look at how the shadow interface has evolved over the past few decades. Desktop platforms set the tone and have been improving this infrastructure for more than 25 years. Windows has had accessibility API since 1997. Any native Windows application built with standard Win32 controls, Windows Presentation Foundation, or WinUI gets baseline accessibility wired in. macOS apps built with AppKit get VoiceOver support through NS Accessibility. The developer has to do some work, labeling custom views, managing focus for complex widgets, but the foundation is there. The screen reader ecosystem on desktop is mature and competitive. NVDA, a free open-source screen reader built by two blind developers who met as teenagers at a music camp in Australia, is now used by over 250,000 people in 175 countries. JAWS, the longtime commercial leader, remains the enterprise standard. Together, they cover the vast majority of desktop screen reader usage. These tools have had decades to mature, and their users had decades to develop expert-level application skills. But here's the key insight. All of that infrastructure, all of those navigation patterns, all of that user expertise, it all depends on one thing. The application has to fit structured data to the operating system. The APIs exist, the screen readers exist, the users exist. The only variable is whether the developer populates the accessibility hierarchy. I want to give you a picture of what it looks like when a platform innovates, because it's truly impressive. In 2009, Apple shipped VoiceOver on the iPhone 3GS. At the time, the idea of a blind person using a touchscreen was considered essentially impossible. There's no physical feedback, no raised buttons, no tactile landmarks. Apple's answer was radical. They built a complete gesture vocabulary on top of the touch interface. Swipe right for the next element, double tap to activate it. Explore by dragging your finger across the screen and hearing each element announced as your finger passes over it. It's been working like a charm ever since. Today, iOS voiceover accounts for over 70% of mobile screen reader usage. A blind person can walk into a store, buy a phone, turn it on, and set it up with little to no sighted help. But here's the thing developers need to understand. This works because iOS has a contract with app developers. If you use native iOS elements, buttons, labels, switches, your app gets accessibility for free. The system knows what a UI button is. It knows the role, derives the name from its title, and tracks its state. Your app is usable with little to no development effort. Android works the same way with its standard view system. Use a standard button, and TalkBack knows it's a button. Use a standard checkbox, and TalkBack announces whether it's checked. There's a clear contract between platform providers and the app developers. Use the native components, and the accessibility hierarchy is populated automatically. When developers break this contract by drawing custom UI elements as raw graphics, by building their own button from a rectangle and a touch handler, the accessibility hierarchy gets an empty node, or no node at all. The screen reader goes silent. Not because the screen reader failed, but because nobody told the system what was on the screen. This contract matters. And it's the contract that most game engines, until very recently, have never participated in. Let's talk about games. I want to start by being honest about why this is hard, because I think the conversation gets better when both sides understand the genuine technical challenge. A typical mobile or desktop app is often built with standard UI components: buttons, lists, text fields, navbars. The OS knows what these are and populates the accessibility hierarchy itself. A typical game renders a single surface of pixels. A Unity game, an Unreal game, a Godot game, they take over the screen and draw everything themselves. To the operating system, your entire game, every menu, character, piece of inventory, health bar, is one big set of pixels. It's a single image. The OS has no idea what's inside it. This is the fundamental difference. When a game engine draws a button, it's not a system button. It's a texture that looks like button painted on the screen. To the OS, there's nothing there but pixels. So when a screen reader user launches your game, here's what they hear. Nothing. Or possibly the title of the window. But none of the menus, the options, or the UI elements are announced, because none of them are in the accessibility hierarchy. This is a structural gap, and closing it requires the developer or the game engine to intentionally bridge the gap between the game's UI system and the operating system's accessibility APIs. For the accessibility experts, this is why saying a screen reader support doesn't translate the same way for games as it does for apps. For apps, the native components do most of the heavy lifting. For games, there are no system native components. Every piece of the bridge has to be built. This is generally an exciting time. At Unity, we shipped native screen reader support for iOS and Android in Unity 6.0. And in Unity 6.3, we extended the support to native screen readers on Windows and Mac. For the first time, a Unity developer can feed UI information into the operating system's accessibility hierarchy across mobile and desktop platforms without building the bridge themselves for each platform. Through our accessibility APIs, Unity now empowers developers to make this transition. Steve Saylor put it best. In his words, building something like that from scratch has to be decided upon early in development, so you have the time and resources allocated to make it properly. Having it in engine can mean the heavy lifting is done for you, and the cost of time and resources now is significantly lower. Well said, Steve. Console platforms are building infrastructure too. In 2025, both Nintendo and Valve introduced system-level screen readers on their platforms. The PlayStation 5 has a screen reader that's been expanding steadily since 2020. Xbox has had screen reader built into the consoles for more than a decade. The Xbox accessibility guidelines lay out exactly what screen narration should do. Read menu text, announce interactive elements with their name, role, and state, and narrate context changes. That language, name, role, and state, is the exact same vocabulary that the accessibility hierarchy uses on every other platform. The concepts are converging. There are the games that aren't waiting for engine support. They're building it themselves and proving what's possible. Diablo 4 shipped with over 50 accessibility features. Blind players have defeated the game's hardest boss using only audio cues. Diablo's lead accessibility designer set the tone. In his words, the only limitation to adventuring in Sanctuary should be interest, not capability. Blizzard built a dedicated accessibility team, brought in the community for testing, and treated accessibility as a design pillar from early development. Ubisoft introduced the memory shards feature, and other studios are creating amazing and innovative features. Naughty Dog's The Last of Us Part 2 shipped with more than 60 accessibility settings. Marvel's Spider-Man 2 includes over 80. Over the last years, competition for prizes at the Game Accessibility Conference Awards has become fierce. These are the AAA studios proving that comprehensive accessibility at scale is achievable and commercially successful. What our team at Unity aims to do is democratize accessibility development by lowering the bar for creators so that every Unity developer can make their games screen reader compatible. Let's zoom out from individual games and look at the ecosystem. The Accessible Games Initiative, launched in 2025, created standardized accessibility feature tags that digital game stores have already started adopting. 700 games on the PlayStation Store now carry accessibility tags. Steam also added accessibility tags. Players can now filter from games with the features they need: screen reader support, audio cues, remappable controls, before buying. The infrastructure layer that mobile and desktop platforms built years ago is now arriving to games. Discoverability, standardization, and platform-level tools. Is the gap closed? Not yet. Most games still render their entire interface as pixels with no connection to the accessibility hierarchy. Most game engines still require significant developer effort to make screen reader support work. But the trajectory is clear. In 2020, if you wanted screen reader support in a Unity game, you needed to use a third-party plugin that implemented screen reader-like behavior into the game, bypassing native screen readers. In 2025, Unity's accessibility APIs are the bridges to narrator, voiceover, and talkback. That's a significant leap from build it all yourself to the engine has the plumbing. I promised this talk would be something you could share with your team. So let me make that concrete. If you're a developer who's never worked with a screen reader, the single most important thing I've told you is that the operating system already has a structured interface waiting for your data. You don't need to build a screen reader. You don't need to invent a new paradigm. You need to tell the OS what your UI elements are, their role, name, and state, using whatever APIs your platform provides. In Unity, this means the accessibility API is shipping from Unity 6. The infrastructure is arriving. What you need to do is to use it. If you're an accessibility expert, the thing I hope you take away is a clear picture of why games have lagged behind apps. It's not that developers ignore accessibility out of apathy, though some do. It's that the structural bridge between game engines and operating system accessibility APIs simply did not exist until very recently. When you're working with a game team, the most productive thing you can do is help them understand what the operating system expects. Roles, names, state, values. Meet them halfway. If you're a studio lead or a producer, the cost argument has flipped. Retrofitting accessibility into a shipped game is roughly 6 times more expensive than building it in from the start. The legal landscape has been shifting over the years, but the strongest argument isn't legal. It's that the tools are better than they've ever been, the engine support is real, and the disabled player community is large. Let me take you back to where we started. You build an app or a game. You spend months on user experience. Every button, every menu, every animation. When you open it, the operating system quietly creates a second version of your interface, a structured description that should be filled in. On desktop, that shadow interface has been present for over 25 years, powering a community of expert users navigating at more than 500 words per minute. On iOS, it has powered a revolution in 2009. A blind person could use a touchscreen for the first time, something that everyone said was impossible. In games, that shadow interface has mostly been empty, a single set of pixels and mostly silence. But it's not staying that way. The consoles are building the infrastructure. The engines are slowly building the bridge. The developers in this audience are building the games. So here's what I'm asking you to do. Share this talk with your team. Share with the accessibility expert who's struggling to understand why implementation is complex. Share with the developer who's never touched a screen reader. Start the conversation. The shadow interface is there. Are you going to fill it in? The tools to say yes have never been better than they are now. Together, we can do more. Please feel free to reach me on LinkedIn at Bianca-Stana. The amazing community of accessibility experts has been improving people's lives every day, and I'm genuinely happy to be part of it. For millions, games remain inaccessible. Let's change that together.